Let's begin. How do you like the question today? I was putting the quiz together. Oh, you don't like it? I was putting the quiz together before coming here. It was a crazy day. My son's school had to close. They told us yesterday. And so, we had to scramble to figure out how to, just kind of coordinate the being with him and spending time. So, because my wife teaches as well, and so I took the morning shift essentially, and it was hilarious. We went out in the snow and built stuff, and don't eat McDonald's before coming to teach. So I'm gonna be a little slow right now, but yeah, I put the quiz like last minute, and I'm looking at this young kid next to me. He's 4. He's running around, and he wants me to fill the air compressor. I have a little air compressor at home, and I exclusively use it for him to just blow balloons and just explode them, or like throw them, make them fly in the garage. And so I was like, what is the purpose of life? I'm going to ask my students, what is the purpose of life? And so that's kind of how the question came up. So, okay. Today, I want to finish with numerical differentiation as part of the numerical calculus umbrella. We're going to keep numerical differentiation under that umbrella. And you will see we haven't done much coding activities with numerical differentiation. We will do one today. Very brief one, just to calculate rates, just a derivative. But the power of numerical differentiation is going to be with ordinary differential equations, which is my favorite subject, which I will start today as well. So without losing much time, let's recap where we left off last time. We learned how to roughly derive a finite difference approximation for a first derivative so far. We took the Taylor series. We said, you could expand it at one of the points. So if your anchor point is xi, you could write the Taylor series at xi plus 1 or xi minus 1. That gives you forward difference or backward difference. Then you can combine the two, and you can get a central difference, which is higher order approximation. You can go even higher order by combining more of those approximations together. So if you were to write a Taylor series at xi plus 2 and combine it with the one at xi minus 1 and the one at xi plus 1, you're going to get a third order approximation, and so on. A lot of formulas out there. If I want to use a higher order formula, I'll give it to you in the exam or the homework, if I want you to use one of those. And then we concluded that, well, at least the useful ones are going to be forward, backward, and central difference. The central difference approximation was second order, which is good, better accuracy. The error is smaller. It's order h squared. H is the spacing or the interval between the points. So the smaller the interval, the faster the error is going to approach 0. And if you were to apply this at a bunch of discrete points or on some interval that's given to you, you're stuck at the edges because you have no more points if you want to apply the central difference formula. Remember, that's where we left off last time. You don't have xi plus 1 at the last point, and you don't have x minus 1 on the first point. So in those cases, you use forward difference at the left point and backward difference at the right point, and you use central differencing in the middle. So that gives you good accuracy across the entire set of data points. Second order accuracy on all of these points except the end points, you get first order accuracy. And the exercise that we will do together now is we're going to program these to compute the rate of COVID infections. Remember, we started with this plot of COVID infections at the beginning. We want to compute the rate of infections per day. So how many people are getting infected per day from the data that was given to us. We're going to use these formulas. In the middle, we're going to do central, and on the last point, we will do backward. On the first point, we will do forward difference. Okay, you can download the data from the numerical differentiation module on Canvas, and the first one is COVID-19 China total daily cases.txt, and the second one, COVID-19 world total daily cases.txt. So download those, put them right next to the Jupyter notebook you're going to be working with, and we will start building this together. Now, we did do a forward difference approximation in the first two homework assignments, the first one, but it was done for a single point and for a known function. F was known. Right now, you don't know that. All you know are discrete values, so you cannot just arbitrarily pick those points. We have to access the array to access the point at I plus 1 and the point at I minus 1 and so on. Okay? So grab those text files and let's create a new Jupyter notebook. So let me see, I'm going to create it over here in the correct directory. Numerical calculus, differentiation in class. Okay, so I'm going to create a new notebook. So, finite difference COVID cases fall 2024 in class. Right, so we'll zoom in a little bit for those of you in the back. And as usual, I'm going to import the boilerplate. You might have SciPy in it, you might have NumPy, a bunch of other things. That's fine, but we've reached a point where we have most of what we need for the boilerplate, like scipy.integrate or optimize and fsolve. You can keep those, carry them along. Some cases you don't need them, you don't have to import them. All right. So let's get started with importing the data. So let me see first if I have. Stay on page. Let me see if I have the data. Nope. That's not it. Okay. Yep, I have the data right next to me here. So let's start by importing the data. And again, I did this for the first time in one of the previous in-class activities to import data from a text file. So we're going to do that again today. I don't expect you to know it incredibly well, but once we hit statistics in the spring, we will learn some more advanced techniques to grab big CSV files and Excel files with data in them, because we're going to rely on data a lot. But for now, let's load up the China cases and the world cases. I'll put the China cases in, so let's call them yi China ch equal mp.load txt. So you're loading just a text file, and that contains COVID-19 China total daily cases. Okay, and if you print ych, what you see, yi, so ch, you'll get, so day 0, let's say you had 547, day 1, 639 cases. So it's just a text file with only one column, because we're assuming we're counting from day 1 or day 0. Okay? And same thing, so let's do, n is the number of points, so let's length of yich. I will need that to create an x-axis of points, which is just going to be a counter. And then we can do xi is just a range going from 0 to n. So xi, if you want, xi contains 1, 2, 3, 4, whatever, all the way to 41 points. So for a total of 42 points. I just need this so I can plot y versus x. And then yi world is equal mp.load txt. And I use the autocomplete a lot. And COVID-19 is type COVID, and press tab, it autocompletes for me. Then I'm going to pick the world cases. And now we use Aaron's mantra: when data is spotted, it better be plotted. Okay? So what do we do when data is spotted? It better be plotted. Thank you for the support of this course and Aaron. And okay, so plt.plot xi, yi, China. Let's give it a square and do label equal inland China, and then plt.plot xi, yi world, and we'll do circles and label equal world, okay? And put a grid, plt.grid. I'm feeling generous today with the embellishments that I'm putting on the plot. plt.label, so I can put the label, and plt.x label. Should have done that at the beginning of the semester to instill good practices in you, but better late than never. Days since outbreak. And then plt.y label, we're going to put COVID-19 cases. And okay, let's plot. So yi world module has no attribute plt.legend. What am I thinking? All right. Okay. Did you download the file?
Yeah.
Put it next to the Jupyter notebook. Davin can help you. Davin, can you help? Sorry. Okay. Okay. So let's say you've done that. So this plot is self-descriptive. We're starting at, since the outbreak counts from 0 or 1, doesn't matter, because we're going to take differences at the end, finite for the derivatives. And we start at around 400 cases, and the cases go up. As you can tell, it was in the first 22 days, it was mainly restricted. Actually, in the first 30 days, it was mainly in China before it started spreading across the world. So you see, world cases and China cases are the same, right? So the China cases are in square blue, and the world cases are in orange. But once it took off and the world started spreading faster, so you could see an uptick. World cases and China cases are still kind of stabilizing over there, okay? So that's kind of what you would draw from a plot like this, that initially both cases are the same because they were primarily haven't spread across the world yet. Okay, so now to compute my rates of change, I'm going to create a function that computes a routine that computes discrete derivatives for these discrete data sets. Okay? And you can apply this to any data sets, really. So let's start with that. Define. I'm going to call it df by dx. And I want this to take xi data and yi data. Agreed? Now, if you want, so I stay consistent with the lecture, instead of yi, let's call them fi. So this would look like fi plus 1 minus fi, and fi minus 1, and so on. So if you want to do that, let's just call the data fi. So those are going to be arrays of the same size, the array of x data and the array of the function data, and we're going to compute the derivatives based on those. All right, so let's start. First, I am assuming that spacing is constant. You could do it with non-constant spacing. We're going to talk about that in a minute, but the programming becomes a little bit more tedious. But for now, spacing is constant. And because in all of these derivatives, I need the spacing h. So I have h here, I have h here, I have 2h. So I just need to compute that h, or the spacing, h, as xi1 minus xi0, or xi5 minus xi4. Doesn't matter because they're all equally spaced. Agreed? Okay. Now I want to store my data in a result, so I'm going to create a result array, and I'm going to make it look like, either one of those arrays. Okay? It's going to be the same size. There's going to be a derivative at each and every point. So I'm going to create an array of the same size. I can get the size of the array and say mp.zeros of size n, or I can use the like functionality, which we saw before, mp.zeros like fi. So what this does, essentially condenses 2 lines of code into one. And if you wanted to create an numpy array of zeros of the same size as fi, you would need to get the size of fi and then create a numpy.zeros of size n. Here, Python automatically does that for you. It grabs the size of fi and creates an array filled with zeros of that same size. Okay? Just a shortcut. Okay, so I'm going to start with the easiest points. Those are the first and last points. Agreed? They're the easiest. So for the first point, result at 0, so that's the first point, is going to be, so that's going to be fi plus 1 minus fi over h, but I is 0, so that's going to be f1 minus f0 over h. Right? So that's the first point. Okay? So derivative at the first point, I equals 0, use forward difference. So that's fi plus 1 minus fi over h, right? Over h, and I equal to 0. Okay? So what that does is fi at 1 minus fi at 0 over h. So let's do the last point now. The last point is going to be a backward difference. So it's going to be f at n minus f at n minus 1 over h. But because I don't want to have to deal with n, I'm going to use negative indexing. Okay? So we'll use reverse indexing. Result at minus 1, so that's the last point, is going to be fi at minus 1, so that's fi at n, minus fi at n minus 1, which is fi at minus 2, right, over h. So derivative at the last point, I equal n, use backward difference, f at n minus f n minus 1 over h. But we use reverse indexing. So use reverse indexing. So n equal minus 1. That makes sense? So with reverse indexing, this last point is located at array index minus 1. So n is effectively equal to minus 1. So you get f minus 1 minus f of minus 1 minus 1, which is minus 2. All right. So now for the rest, the remaining points. What do you think we should do? How would we do it? Pardon me? Central difference, agreed. But how are we going to implement that? For all of the remaining points. All of them. Ashton? Okay, is there something better than a for loop? Daxton?
Array appending, where you do something like
Appending? Slicing, yes. We're going to do array slicing. We love slicing in this course, okay? Why am I teaching you slicing? Because array slicing in a few years is going to be, you're going to be able to run it on GPUs and multi-processing. The for loop, you have to program that, you have to hard code that. Once you upgrade your new Pythons into these new computers coming up, it will automatically parallelize it for you. It will split it into many processors and do it faster. Okay. So with slicing for central differencing. Okay. So for central differencing, we are left with these points on the interior. Agreed? So my result is going to live on the interior points, or the subset of the interior points. What is that subset? It's from 1 to minus 1. Agreed? So that's the subset array that is going to contain the derivative at the interior points. So this will be result from 1 to minus 1. Okay, and again, if you're like, okay, I'm confused about this, I don't understand, create a little array, say A is equal numpy dot array of 1, 2, 5, 6, 76, okay? And then say A from 1 to minus 1 is going to give you these guys in the middle. We excluded the first point we already calculated here, right? And and result 0. And the last point we already calculated, so I need to focus on these points now. All right, so now, again, thinking in terms of subset, I need the subset of all the points to the right minus the subset of all the points to the left over H. That's what the formula is telling me. The formula is telling me I need fi plus 1. So if you're at any point I, fi plus 1 is all the points to the right of point I. And fi minus 1 is the subset of all points to the left of fi. So we did this before with the slicing, okay, where I had slides showing the arrows, etc., how we combine them together when we're doing the convergence rate for the error. So that's what we need to use here. Okay. So the subset of all the points to the right is going to be fi starting from 2 all the way to the end minus fi starting from the beginning all the way to minus 2. So that gives us all the points to the left, and then over H. If you make a mistake here, it will throw an error very quickly for you. Okay. Now, if you're confused about this, again, come here and say, okay, A from 2 to the end is going to give you, where is my array? Okay, array A from 2 to the end. It gave me 5, 6, 76, all the points to the right, because I'm starting at this point here. The first derivative I want to compute is this guy. So I need to take all the points to the right of that guy minus all the points to the left. Now, when you combine them together, it's going to give you the derivative at each one of those points in the middle. Once you're done with that, then you return. No, we forgot we made a mistake here. It should be over 2h, okay? And then we're going to return result. Okay? Delete this, delete this. Now, so let's do it. Let's do the rates for China. We have df by dx, xi, yi China, and the rates for the world. We have df by dx, df dx, xi and yi world. Once you compute that, it just computes it, and then you can plot it. plt.plot. So let me copy this from here. Now I'm plotting rates China versus xi and rates world versus xi, and then rate or COVID-19 infection rate. So how many persons per day? When you plot this, you see something like this. So initially, I don't know, probably, so this is a very large scale. So 1,000 is over here. So by day 5, you had 1,000 people being infected per day. Then by day 10, you had about 2,000. Then it peaked to 4,000. It started dropping a little bit. Maybe some people started developing immunity after 14 days, or reporting was all over the place, right? Then you have this peak over here where suddenly there were a lot more reports coming in. So if you look at the original plot, over here, the cases spiked. We went from 40,000 to 60,000 in 2 days, or 1 day even, right? 1 day. And so obviously the rate is going to spike. So this is probably an outlier over here. I wouldn't trust it much. But then you continue with rates declining in China and then stabilizing, right? So here you're getting to about maybe 10 infections per day. You know, I don't know how much you would trust the data, but then I just pulled these data. It's a good example to work with. But then these cases here in the world continued climbing. Not the cases, the rate of cases. So you're hitting 2,000 people by day 40. So that's February, March, maybe first week of March or first week of April, I think, you get 2,000 cases per day in the world, people being infected. So it's spreading pretty quickly. Eventually, it will stabilize. But that's how I would use these, finite differences. Again, the finite difference work we want to do, we're more interested in differential equations than just computing rates, because it's an easy problem to solve doing this stuff. It's not inventing the wheel or anything crazy. But it's the formulas that I'm interested in. Okay. So let's go back and finish off. We did this. And yet last time I discussed the issue with this case is that in the middle you're doing second order, and on the edges you're doing first order. So you have a mixed error in your result. For this problem, it's not going to be an issue because the errors are independent of each other. You're doing the derivative at a point. But once we go to differential equations, the nature of differential equations, all points are actually communicating with each other. You will see with heat transfer, with chemical reactions, there's communication at different points. And so if you commit an error even at one point, it's going to propagate everywhere. And we say in practice that your highest, the strength of your chain is as strong as its weakest link. And that's what will happen with differential equations. If you have loss of order even at one point, you're going to lose order everywhere. But in this case, it's not, because they're not communicating with each other. The derivatives are independent of each other. So, your second order in the middle, first order at the ends, and, you're fine. Okay. So this is a summary here now of the methods we learned and a couple other methods that are different order. Well, same order, sorry, but they look differently. And I'll explain why. So the first forward difference, that's the formula Fi plus 1 Fi over delta x. It's order delta x. Delta x is the same as h. Don't confuse the two and make a fuss about it. Forward difference, does it require constant spacing? No. So the forward difference doesn't require constant spacing. Neither does the backward difference. That's the beauty of those two methods. But the disadvantage is that they are first order. So they're errors. They commit the worst errors compared to all the other methods. Then we got to central difference, and it was second order, but the central difference scheme unfortunately requires constant spacing. It's just from the way the formula is constructed. You need to have Fi plus 1 at the same distance from Fi as Fi minus 1. Otherwise, you cannot do the combination of the Taylor series. You cannot cancel out the h's the way we did, right? With the forward and backward difference, we only needed one Taylor series. With the central difference, we needed two Taylor series. And so they needed to share the same h value to be able to cancel them correctly. Now, you might say, okay, what if I have constant spacing and we did second order in the middle? Can't we find a way to do second order at the endpoints without overstepping outside into the domain? Yes, of course. And those become higher order forward or backward differences. And you see this is a second order forward difference method. So you could use this on the leftmost point, and you'll see it reaches into, so you're at point I, and it will depend on I plus 1 and I plus 2. Okay, so it reaches 2 points into the domain just to be able to get you second order. Same thing for the last point. You can get a higher order backward difference, which is second order, and it reaches into the domain, 2 points into the domain. So you're at the last point, and you reach first point interior, second point into the interior. Okay, they're just formulas. You apply them. We can do the same also for second derivatives, but I will just give you the formulas here, and you don't have to memorize them. Just know that they exist. I will give them to you in the exam or in the homework. I'll tell you use this formula or that formula. But for you, you need to recognize what Fi, Fi plus 1, Fi minus 1. I might give you a formula with Fi minus 5. That's okay. Point I minus 1, I minus 2. It's 5 points away from point I. Okay? And with second derivatives, it gets a little bit, you need more points to compute the second derivative. And the way you build those, similar, but you need more Taylor series to combine with each other. So for example, I'll just talk about the central difference for a second derivative. That's the most commonly used formula. That's the one we used in heat transfer when we did the heat transfer problem. Remember when I told you approximate the second derivative with this? So we're getting very close to learning how we do that with the ODE. But this formula required Taylor series at fi plus 1. Fi is just fi, and Taylor series at fi minus 1, and we combine them to get an approximation for the second derivative. Previously, we combined them to get an approximation for the first derivative. Okay, so this is a different combination. And they all require constant spacing. All of these methods require equal spacing between the points. Okay, and those are the formulas, and that's it. What remains in the slides, I give you an example of how you can build the higher order, the approximations for the second derivative, etc. You're welcome to look at those. And I'll let you take a 3-minute break before we start on ODEs, okay? So you don't fall asleep on me. ODEs is very, 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 very important topic, okay? And if they didn't teach it, if you took it in math or you didn't take it in math, hopefully you'll get a fresh perspective from it here with me. All right, go. Take a break. Sorry, 1 second. Okay. I need to charge this. It's running out of battery. What's up?
I was wondering if I can see the plot read
The what?
cell for the original plot that we did because I have my
Oh, for the Jupyter notebook?
yes because
Yeah.
file
Okay, so yeah.
situation,
Which
the
slide?
first one.
Okay, hold on. This one?
Yeah.
Okay.
I don't know what I'm doing. I haven't downloaded it.
Did you? The file is next to you, right? Is next. It's not found. It says file not found. So where is this Jupyter notebook? And it needs to be living in the same directory
Oh,
as that notebook. So right next to it.
okay. Because I have it. This Jupyter notebook is in my numerical file.
Yeah. So move them over there. They need to be next to each other, or point to it. Point to it. Okay. Okay, shall we resume? Right, how many are we missing? 1, 2, couple. 1 more minute. So I tell my son, give me 5 minutes. He said, okay, 1, 2, 3. Like, no, you have to count to 300. It's like, why do I need to count to 300? That's 300 minutes. But then I tell him, give me 300 seconds. It's like, 300 is too long. Oh my gosh. All right, let's resume, please. Let us resume. Okay, so first, Has any one of you seen those creepy lobster merch in the ICC Center? Okay. Have you seen the? I might have brought in real lobsters at one time, but no. Have you seen the merch, the cup, the hoodies? Some of the students wearing the hoodies. Okay. I'm excited to tell you that today you will see for the first time why the lobster theme is so important in numerical methods. Our first discussion on lobsters will occur today. Okay. And why I chose lobsters, we'll explain why along the way. This is one of my favorite topics. Regression was a favorite topic. Differential equations is even more favorite than regression or data analysis, because in my nature I enjoy the intellect, the theory, and modeling, and differential equations are the key to modeling the world, versus data science or statistics, where you're collecting data and trying to understand the world just from the data. And so two different ways of looking at the world. They're both equally important, but I want to give you a little overview here of where we started, and I'm going to plot on the x-axis, your independent variable, on the x-axis what we've learned, and on the y-axis your knowledge, or what I hope your knowledge was, and what you accumulated. So we started with error analysis, and I'm going to list the x-axis first. And then we did algebraic equations, so solving linear and nonlinear equations. Then we did curve fitting and data analysis, very basic, interpolation and regression, right? And then we just finished off with numerical calculus, and now we're going to hit differential equations. And if you see the theme, here we learned how to solve algebraic equations. Today we're going to start learning how to solve differential equations. They are very tightly connected together, those two topics. Okay, very tightly connected together. Now, if you plot your knowledge, this is what I expect it to be, and what these topics are contributing to your knowledge. So how you compare your knowledge, you compare yourself today to yourself yesterday. You know, yourself at the beginning of the semester. Don't compare to others, be inspired by others, etc. But compare yourself, like, are you moving in the right direction? Are you increasing your knowledge as you go through your courses, through this course and other courses? And what I expect to see is this, okay? What I expect to see is this, especially with differential equations, because differential equations are going to change your mind, your perception of the world. Now, obviously, it's depending on how they're taught, that could make a difference in how you appreciate differential equations. I like to call them the tuning forks of engineering science. So they are so fundamental to modeling and understanding the world. Some people take 7-8 courses just in differential equations to be able to even comprehend and understand how to work with these things. Okay. My objectives in these last lectures is to try to convey to you an intuitive appreciation of differential equations in a very practical approach. I'm not going to talk theorems or lemmas or existence. The mathematicians have done that for us, thankfully. And in engineering, we know most of our models that are based on differential equations, they exist. They give us reasonable solutions. So I want to give you an intuitive appreciation of how differential equations operate, how to build them, at least for ordinary differential equations, and then a very practical, applied, hands-on way to solve them. Because next year, and you can ask your favorite TAs here, next year you're going to be doing heat and mass transfer, and you're going to be solving nothing less than one differential equation a day. And if you know the tools you learned here, you don't need any other tool. You don't need Excel. You don't need anything. You can do this very effectively, as my TAs are agreeing over there. Yes, thank you. Okay. Right. So our learning objectives, the slides are kind of wide over here. I haven't changed them because I used to teach this over a green screen. And that's kind of when we shut down during COVID, I had to put this on a green screen, so I had to have some room to walk around the slides and never change them back to a smaller format. So there's some white space around the edges, but that's okay. So at the end of this chapter, I hope you'll be able to define a differential equation, define and identify what we mean by dependent, independent variables. So now this is similar to what we were talking about, y versus x, etc. But now you will see it in action differently, where you see a derivative of temperature versus space, or a derivative of density versus pressure. You'll be able to tell which one is the dependent, which one is the independent variable. What are the coefficients? What's the right-hand side of a differential equation? You'll distinguish between a partial differential equation, PDE, and an ordinary differential equation, ODE. Would have been really cool if they called them extraordinary differential equations rather than partial. But that is what it is. Identify and classify ODEs as initial value and boundary value problems. So we will only talk about ODEs in this class. There's too much to go to PDEs. But if you know ODEs very well and how to solve them numerically, once you hit PDEs, it will become apparent. So we will learn with ODEs what we call initial value problems, which are differential equations in time only, versus a boundary value problem, which is a differential equation in one space dimension. When you combine the two, time and space, you get a PDE. So you combine the two solution methods, and you'll be able to solve a PDE. Describe the meaning of terms in an ODE: rate of change, a second derivative, it's a diffusion term, is it a convection term? Order reduction for high order initial value problems. So you'll see that there's a little trick. For all high order initial value problems, you can convert all of them into a first order system of ODEs, which is standard to solve. And then create Python code to solve a single ODE or a system of ODEs using ODE integrate or ODE int. So I'll teach you the tool in Python. We might do it by hand. We'll see, depending on time. But using the tool in Python, you'll do it by hand analytically on a pen and paper for sure. We might programming in Python or just use ODE int. We'll see this year. Create Python code to solve single ODEs using your own routines, maybe. Should put that in red. Use explicit and implicit finite difference methods. So a lot of things to learn about. But at least I'm kind of listing the objectives for you as you plan your learning guide for the end of the for the end of the semester. And we'll calculate numerical solution for initial value problems or systems of equations. We use finite difference methods to calculate, to solve boundary value problems, identify when the right-hand side is nonlinear. So now we're going to tie this back into nonlinearity, and then you end up with like systems of nonlinear equations, which is like the worst of the worst. If you thought it was hard, this is like 100 times harder. And calculate numerical solution for an implicit method using with a nonlinear right-hand side using Newton's method. So again, we might touch on this or we might not, depending on how the semester goes. We'll see. But at least I will cover the foundations for you to have a healthy relationship with differential equations, so that next time you know where to go to and what to consult when you're faced with an ODE. All right. What is the differential equation? What do you know? So first, who is currently taking differential equations? Wow. ODEs, right? In math, in the math department. Okay, where are you at? Or are you all in the same class? Nice. Okay. You can take over the class, essentially. So where are you at? What are you learning right now? Do you remember?
I think in my class we're learning like how to solve like ODE systems using like eigenvalues and whatnot.
Okay, so you're doing some analytical methods, etc. Yeah, variation of coefficients. Did you learn that? Okay.
Yeah.
Okay. Okay. Do you do time-dependent, space-dependent ODEs?
We've done vector spacing, so I'm not sure if that's
okay. But you just dealt with like y prime equal 3y squared, for example, y double prime. So just kind of what is y? Who knows, right? But at least, they're kind of showing you that. Okay. So who has not taken ODEs or differential equations at all? Okay. Who has taken ODEs? Okay. Okay, so it's a mix. It's a mix. That's why I leave this topic to the end, because hopefully by this time most of you who are concurrently taking ODEs have seen what an ODE looks like. So So you should be able to define a differential equation. What is the differential equation? Could be a technical definition or an intuitive definition. You are a differential equation. We technically are differential equations. Our bodies can be modeled as differential equations. Daxton.
Isn't it just an equation with like a derivative of a variable that you don't know?
But derivatives in it. Yeah, and you don't know the variable, right? Okay. Any other definitions? Like even what you perceive a differential equation is. For those who are taking currently the course, didn't you start by like learning what is the differential equation? Okay. All right. Well, that's good for me because now I get the chance to teach you that. So next year is like, well, Professor Saad taught us that. Okay. So we'll begin with a formal definition. You know how much I hate those, but we got to do the formal definition, and then I'll ask why, and it doesn't make sense, and let's kind of dissect what it means. And a differential equation is simply an equation that has derivatives in it. So I call differential. Okay? It's an equation that has derivatives in it. Derivatives of some quantity, we call that variable, sure, but derivatives of some quantity rather than just the quantity itself. So a differential equation is not a standard equation. A standard equation is like a formula, right, where you could have y cubed equals 3 sine x. That's technically a formula. But when you have dy by dx equals 3 sine x, that's not a formula, that's a differential equation. That's worse than a formula, right? So a differential equation, this is an example of a differential equation, looks like this. This one, for example, has two derivatives in it, this derivative and this derivative, and has a second derivative and a first derivative. They're both with respect to x. They have a bunch of coefficients on them, so let's define those. We define the thing that's being differentiated. We call that as our dependent variable. Just get the formalism out. Everything that's been differentiated with respect to, so in this case x, whether x squared, x cubed, doesn't matter. This is your independent variable. And these guys are your coefficients. Okay, they're the parameters of the differential equation. They could be constant, or they could be function of the dependent or independent variable. So k and u can both be a function of t and x, both or either. Okay? They could depend on that. I'll give you an example. Viscosity, which is the ability for a liquid to resist motion. So honey versus water. Honey is a liquid that has more viscosity than water. It's kind of hard to push it, hard to smush it, right? The viscosity is typically depends on the temperature. So as you heat the liquid, as you heat the honey, what happens to it? Becomes softer as the viscosity goes down. Okay? So that's an example. But the viscosity in the model differential equation for honey shows up here, like in this term. And it's a function of temperature, will be a function of temperature. Okay? So now, why do we develop equations with rates of change in them? That's the question. Like, why are we learning differential equations? To me, that's the exciting question. Not that they exist as fun mathematical tools, and I'm excited about finding an exact solution that's useless, right? I want to understand why do we develop equations with differential equations, with derivatives in them. Again, I'm going to give you a formal definition, but then we'll go through a lengthy example, and I'll introduce to you the mighty lobster, and then try to explain why we do derivatives. But in a nutshell, and I know you might disagree with this statement, but as you learn more in your engineering career, you'll get to appreciate it. It is easier to describe natural laws and complex phenomena by finding relations between rates of change of variables rather than the variables themselves. It is easier to describe the rate of change of heat in a wall or something rather than the heat, the temperature itself. because we don't know where to start with that temperature. I'll give you an example of why this is the case. Okay, so let's do an example, and this is a motivating example for studying differential equations. So don't go and say lobsters are differential equations. No, it's just a motivating example to why we need differential equations. Okay, because again, remember that it's going to be easier to describe complex laws when you relate rates of change rather than using directly the variable themselves. So this will become clear as we build this example. So I will start with an example from population dynamics. If you've taken ecology or zoology, any course in that, or are interested in that, you've probably seen this, how populations grow. And it's a great example to set the stage for why, again, I'm answering here the question, why do we need differential equations? Just a simple example for that. And I picked this example because it's easy to reason about. It just requires basic knowledge of thinking. Like I passed it by my mother, who is illiterate, and she was able to understand with me kind of how to do the numbers around it. So make sure it's an easy example. Okay, so consider a population of this unicellular organism called the paramecium. In this population, the individuals divide once per day. So they just split. Okay, one paramecium, I guess paramecia is many parameciums, right? So one paramecium organism splits once a day into. And then those, they also grow, and then they split, and they keep on splitting, right? So over time, if you're starting with one individual, after a day you're going to get 2, and then you're going to get 4, and so on, and then you get this kind of exponential explosion in it's cell splitting, essentially. So if we start our population with P0, let's say it's 1 individual or 10 individuals, it doesn't matter, it's called P0. After 1 day, you have 2 P0, right? Because now they doubled. Okay? After 2 days, you have 2 times P1 or 4 times P0. Now, what is the population of paramecia after T days have passed? Go. Going to build this together. Okay. So they double after each day. So get me a recurrence formula for the population after T days. 100 days, 500 days. Pardon me?
The question is like, oh, would you rather have this $1 million now or like a penny that doubles every day?
Yes, that's right. I'd rather have the penny that doubles. Okay, so after 2 days, it's 2 to the power 2. After 3 days, it's 2 to the power 3. After T days, it's 2 to the power T, P0. Okay, okay, good. So, and again, I'm like not going to ask you about population dynamics. I'm just trying to make you work through the math to show you how hard it is to get to the answer that we're going to try to get to. So after 3 days, you get 2 to the power 3 P0, and after T days, you get your population of paramecia after T days. It's PT, 2 to the power T P0. You can verify this. After 1 day, you have 2 P0. After 2 days, you have 2 squared P0, and so on. It's kind of simple recurrence formula. Okay. Now, in general, the rate of growth could be any number R, because populations, just the paramecium is unique because it splits in 2 every day, but populations behave differently. They might double in a year, or they might quadruple. Some of them might die off, etc. So to generalize this, we consider a population of lobsters. Okay? Now these lobsters are living in the ocean. They're hanging out. They're kind of courting each other. Some of them are dating. Some of them are getting married. They're making babies, right? You know, it's the life of the lobster. You know, they're doing their thing at the bottom of the ocean. We go to that lobster. We pick one, and we're like, oh my gosh, you know, dad is gone now. And so, anyway, now if you don't eat meat or fish, you can substitute this with the paramecium or like a vegetable or something. But we'll stick with the lobster, and that's the beginning of the lobster discussion. They're like interesting, and they're kind of a little creepy. Like imagine you have like a bunch of lobsters crawling here. They're like little cockroaches, right? But then when in the ocean, they're so beautiful and majestic. You look at them, like imagine like having lobsters on the floor of your kitchen. They're just kind of weird. So I have a love and hate relation with the lobster. Anyway, so in general, like I said, like these lobsters are not just doubling every day. There's an intrinsic rate. So in zoology, they call this an intrinsic population rate. On average, a population of lobsters, how is it behaving? It's not doubling every day. It could be like times 1.345 every day, right? So it's like it's not an exact integer number. So the way we like to write this is, in general, the population grows as r to the power t p0. R could be 0.1, could be 5, could be, for paramecia, it is 2. Okay. Now, specifically, and because these people have studied this for a long time, r to the power t, they like to write it as e to the power rt with a lowercase r, so that they are in exponential regime because it's easier to differentiate the exponential, etc. So they just write r to the power t as e to the power rt, which is the same thing because lowercase r is log capital R, and this lowercase r is called the intrinsic rate of the population. It's the same thing, just two ways of writing the same equation. This equation is the same as the other one, except now I have an exponential. It's easier to differentiate an exponential, okay, versus r to the power t. And the little r is called the intrinsic growth of the rate of the population. It's like compound interest for your money in the bank if you have any. Okay. Now, all right, so we take now this equation. Pt is equal P0 e to the RT. Now you have three behaviors here, depending on r. So if you were to plot the population of our lobsters versus time, we have three options here. If r is greater than 0, so if they're making more babies than the population is being eaten by or dying, then the population is going to grow. Agreed? It's an exponential, right? If r is exactly 0, then there's an equal amount of baby lobsters being born as lobsters dying. Right? So the population is fixed. It's not changing. And if r is negative, then the population is in decay and it's in decline. Okay, so think about population rates, right? So, the replacement rate, 2.3 or something, right? If every, family is only making 2 babies, that's not replacement rate. It's a population in decline. You need to make more. That's kind of the same thing here, because that's the typical behavior of populations. Okay? Okay, great. So now, in practice, populations are actually bound by available resources and competition and predation and all sorts of things. And typically, they look like the graph to the right. So take any population in a ecosystem, lobsters, whatever, birds, rats, etc. With given availability of resources, they populate, and then they reach a steady state, and they stabilize. So it looks like this. Initially, there's exponential growth, and then it flattens out, okay, at some number k. And that k, it's called the carrying capacity of the, again, you don't need to remember that. I'm just using I had a student who has taken a course in zoology, and he taught me all of these words. So it's called the carrying capacity of the population. Okay. So anyway, the point is that the population grows like this. All right. So now, given what you know about the population, that it grows as r to the power t times p0, right? So get me a formula for this curve. And don't look at the slides. Okay? So I know you'll be cheating. So the population is reproducing as r to the power t or e to the r, lowercase rt. How can I trigger that stability, that flattening at the top? Use k to your advantage. Don't look at the next slide. No, give it a serious thought. Give it a serious thought, please. So you could multiply it by something that goes to k minus 0, k minus 1 or something, or like come up with some formula. Can you come up with any formula? Some people are leaving. So we've seen a question like this before.
In this class? No.
We've seen a question like this before in this class of a similar spirit. A question in a similar spirit. Remember the guy trying to walk in the flooded pipe? What was the answer there? Told you to find the height analytically. Okay. It's a difficult problem to solve, isn't it? Because there's no, unless you're like Chandrasekhar or Einstein, there's no obvious way to get this formula, even if you're observing this. There's no obvious way to get a formula for this. You could try to say, okay, I'm going to multiply it by something that is exponential and then decays k. Okay, good luck, but it's not going to be an exact representation of the real system. The actual formula is this. P0k over P0 plus k minus P0 e to the minus RT. There's no way you'd have figured that out, right? No way, you can't figure that out. Now, think about it when you have k minus P0 over here. It gives you that difference from P0 to k, right? Now, as t approaches infinity, this becomes vanishingly small, so almost 0. So you get P0k over P0, which is k. So indeed, this as time approaches infinity, this formula does flatten out as k. Okay? But how did I obtain this formula? Not from Google. Well, initially I started with Google. But you can just say I asked Google to give you that formula. Okay. So why I did this exercise right now is to show you that, okay, so there are some cases where you can't just come up with a formula for the system. So how can we describe this system? We can't come up with a formula to describe it. How can we describe it? Okay? Let's take another approach. And instead of looking at the population itself, let's see if it's easier to look at the rate of change of the population. That was my premise from the beginning, that it is easier to work with rates of change of a quantity rather than directly with a quantity. This is the example, that's the objective of the example. Instead of working directly with the population of lobsters, let's look at the rates of change of the lobsters in that population and see if we can come up with something that potentially could give us this formula. Okay, we have to start with a warm-up. So first, consider a population of lobsters with an initial size of P0. Assume that the birth and death rates of lobsters is equal. Now I'm talking about rates. Okay? So that their population remains constant over time. Now develop an equation for the rate of change of the lobster population over time. So dP by dt. Rate of change of the population over time. I'm saying that it's not changing. I'm telling you it's not changing. So what is an equation for the rate of change of the population? I'm telling you it's not changing because there's an equal number of birth and an equal number of death. So the population is not changing. Therefore, what is the rate of change of the population? 0. Okay, yes. It's going to be 0. This is a warm-up exercise. Because the population P of lobsters does not change over time, then dP by dt is equal to 0. Okay? Now, you could have said it's not changing, therefore P is constant. Yes, that's fine. But that's an easy problem, right? But I want to train you here to start thinking in terms of derivatives. So now you say dP by dt is 0. The solution to this equation is that P is a constant, as we expect. Agreed? But I want you to start thinking of working with derivatives, with rates of change, rather than the quantity itself. Okay? Okay. Let's take it up a notch. Now assume that, again, we have dP by dt. We're always looking at dP by dt. And we're going to change something on the right. At the beginning now it was 0, so the population is constant. Now assume that the lobster population changes at the rate r, so that r times p new lobsters are added or removed per unit time. That makes sense. If you have 10 lobsters and they're kind of multiplying, right? And if the rate is like, 1.5 lobsters per every pair, right? So it's going to be 1.5 times those 10. Or times 100, right? Or times 1,000. So the rate of growth is going to depend on the current size of the population. So now this is saying that RP new lobsters are added or removed per unit time. R could be positive or negative. Now develop an equation for the rate of change of the lobster population over time. So dP by dt. I'm saying that the rate of change is RP. So give me the differential equation. That's your first differential equation that you've created. R times P new lobsters are being created. Remember, R is the growth rate, but it depends also on the current population size P. So it's R times P. Right?
Right, okay.
Yeah. If there's more lobsters, then if there's 100 lobsters, you're going to end up with 200. If there's 10, you're going to end up with 10, right? So it's not R, it's R times P.
Okay.
And you got it. Now solve this. Okay, so what do you got? dP by dt equal R. R. Okay, some people are saying R. So, but then if you say dP by dt equal R, then if you have a population of 1 million lobsters or 2 lobsters, they're growing at the same amount is growing, right? Doesn't make sense, right? Because the 1,000 lobsters are gonna, if they just have one baby, each pair, they're gonna be 500 lobsters versus the 10 lobsters are gonna have 5. So it's not R, it's R times P. Okay, and I'm telling you here, the rate is R times P lobsters. Okay? So the rate of change of the population will be equal to the change in population. The change in population is R times P, right? That's how many lobsters we're adding every unit of time, every second or every minute or every day, or removing. So really the rate of change is equal to RP. If 10 lobsters are being, of RP lobsters, if 10 lobsters are being born and 5 are being, are dying, then the net is 5 lobsters. So dP by dt is plus 5, right? So what I'm saying here, this is how many lobsters are added or removed is exactly R times P. So the rate of change is R times P. Okay? Now solve this equation. What is the solution? It's P0 e to the RT, which is the formula that we built with recursion. Except here we approached it from a different perspective, thinking only about rates of change. Right? So you agree that this is the formula we obtained earlier, P0 e to the RT. If R is positive, population is growing. If R is 0, it's flat. If R is negative, then it's decaying. But I obtained this formula from a differential equation rather than doing the recursion. Rather than thinking directly about the population, I thought about the rate of the population. And the solution to the differential equation was the formula that we cared about. Okay, so let's do this last one. It might be a little hard. Now I want you to apply this concept to model this system. So now we have a population with a carrying capacity. Okay, and it's fine, we'll work on this together. Except now that you still have R times P, but that population is going to slow down as it reaches K. So I want to replace R with R times something, such that this something, when the population reaches K, it becomes 0, right? Because we want it to be flat. So once the population reaches K, there's no rate of change anymore. Okay, so here's what I'm going to do. I started with dP by dt is Rp. Now my R is actually a function of the carrying capacity. So if instead of R, I put R times K minus P, when P is equal to K, this becomes 0, and the right-hand side becomes 0. So then dP by dt becomes 0. So see what happens. When P equal K, this whole thing is 0. So you get that flat thing at the top. When P is less than K, you still have the standard exponential growth. Now, what's important here is that the solution to this equation is this formula. And that's how I obtained this formula, is by looking at that equation. Okay, you might think, it was a little hard to model that, but it's easier. At least you have some guidance there. Say, okay, the rate of change, it's growing, but it's going to reach a point where it's going to slow down. So I need to have a switch, K minus P. When P is equal to K, it becomes 0. That's the reasoning you will eventually develop. I don't expect you to know it now. Don't feel bad if you didn't figure this out. It's a difficult problem, but it's less difficult than directly thinking of this formula. Okay? So, there's a philosophical point over here, and that is that, and that's why I call differential equations are the tuning forks of engineering science and physics. And I still claim that it's easier to relate rates of change than it is to develop algebraic formulas for a quantity. This is, if you take something out of this lecture, is this. The solution of a differential equation is a formula. The solution of a formula is a number. So in terms of the hierarchy of abstraction, differential equations are formula generating things, right? Entities. You can think of a formula just by kind of multiplying things and, okay, guessing something. A more superior way or abstract way of developing formulas is to develop a differential equation itself. Because the solution to a differential equation is a formula. The solution to the formula is a number. Okay? There's also one more hierarchy. Because the differential equations are the solution to something else. And that's called variational calculus. So those are the foundations of physics, where we say in calculus of variations, we say, for example, how do you minimize the action or the kinetic energy and gravitational energy? Just from that concept, you do some math, and the answer to your math are Newton's laws, which are differential equations. So calculus of variations, the answer to calculus of variations are differential equations. The answer to differential equations are formulas. The answer to formulas are numbers. Okay? I hope you can appreciate that beauty. If you're mathematically inclined, you'll appreciate that. Yeah.
Where's partial differential equations?
Same. They fit with, it's differential equations. So partial or ordinary. Okay? And we're done. Look at that, like perfect timing. Okay, so just, okay. All right. Thank you, everyone. I will see you on the exam next Tuesday, right? We have an exam. Okay.